Hi everyone, welcome back. We're going to talk today about correlation analysis and linear regression. You've, so far, we've looked at the relationship between a categorical variable and a continuous variable when we looked at t-tests. We've also looked at categorical variables against categorical variables and when we're doing the chi-square test. But what we haven't talked about is when we have two interval or two continuous measures, how do we assess the relationship between those? And that's going to be the topic of correlation analysis. Linear regression also can tell us the relationship between two continuous measures, but it also can do a lot more, as we'll see. But for now, we're still kind of stuck in the realm of bivariate analysis, and we're going to start to make the leap into multivariate analysis very soon. But let's start by looking at correlation analysis. So correlation analysis is used to explore and test for linear associations between two continuous or interval variables. Specifically, we'll calculate a correlation coefficient called Pearson's R, which allows us to assess both the strength of the association and the direction of the association between two continuous measures. We're going to start to practice looking at some scatter plots, which are the ways to visualize correlations, and calculating Pearson's R to better understand the relationship between two variables. So a scatter plot is simply a pairs of observations of one variable and another variable plotted in a diagram, and it can be used to visualize the relationship between two continuous or interval measures. It's always a good idea to examine a scatter plot before proceeding to formal correlation analysis, because we can start to detect to see if there are any nonlinear relationships. So what does it actually look like? So here's a scatter plot that I did in SAS Studio using the same data set that you've been using so far, which is the heart data. And I did a scatter plot of weight against height. And as you can imagine, we would expect there to be at least some relationship between height and weight, definitely not a perfect relationship. And that kind of plays out in what we see here. So for every pair of observations, so for each individual in the data set, if we take their value on height and their value on weight and we plot a point, this is what we would see. So I don't know what your eyes are telling you as far as what this looks like. It kind of looks like a cloud of points. But overall, you could see as weight increases or as we go up on the x-axis, height is also going up slightly. And the reverse is true as well. As height increases, overall weight is increasing. We're seeing fewer points down here. Okay, we see a few, but overall it's moving in that direction. So this is not really going to tell us absolutely everything we need to know about the relationship, but overall it looks like there's sort of a positive relationship between height and weight. So this is a first step to just kind of visualize relationship, and then we can describe this relationship and how strong the relationship is using the Pearson's R correlation coefficient. Notice here in the syntax that I used to generate this plot, which is part of the graph features, I simply told it, give me the weight variable as my x and weight or height as my y variable. Conceptually, it might have been better to choose weight for my y and height as my x, considering that it's height that's driving weight in this relationship as opposed to the other way around. But in a correlation analysis, a pure correlation, it really doesn't matter which we put as our x or y. As we'll see when we calculate a correlation coefficient, it's still going to give me the same value regardless of which one I choose. And conceptually as well, when we do correlation analysis, we're not really looking for causality, we're just looking for associations between two variables. So a positive value for Pearson's R greater than 0, that is, indicates a positive linear relationship. As the value of one variable goes up, the other goes up, just like we saw with height and weight. That would be considered a positive relationship. A negative relationship, or where Pearson's R would be calculated as less than 0, indicates a negative or inverse relationship. as the value of one variable is going up, the value of the other variable is going down, okay? So both are possible and both are equally important to characterize. So the strength of the association is indicated by the absolute value of the Pearson correlation coefficient, which goes from -1, that would be a perfect negative correlation, to +1, or a perfectly positive correlation. And in the middle is 0, and that means no relationship. It'd just be a cloud of points on the scatter plot. You wouldn't be able to see any pattern at all. So a -0.75 correlation would be just as strong in terms of absolute effect or relationship as a positive 0.75. A -0.5 would represent a negative inverse relationship, and a positive 0.5 would represent a positive relationship. We're going to see these in the diagram format or scatter plot format. So a perfect positive correlation, again, we're putting points of X and Y for each observation, each person in this study. And you can see that all the dots are along a single line here. This was probably actually measuring the same thing using just a different variable, basically measuring the exact same phenomenon. So maybe something like height in inches against height in centimeters, we would expect to have a perfect correlation between those two measures. So rarely would we find a correlation as strong as this, but this would be a perfect positive correlation. Compare that to the scatter plot that I showed you for height and weight, and you can see the difference. In a moment, we're going to calculate what the R value would be for our correlation coefficient for the height and weight. Okay, this would be a slightly more realistic situation. This would be a very strong positive correlation. You can see here that it almost looks like a line, but there's a little bit of scatter, okay? So as one variable is going up, the other is going up proportionately with very little deviation from that. This would be what a correlation of 0.95 would look like. As we get to more and more scatter, we can see that though overall there's a positive relationship here, you can see the points are more scattered around that line that you can kind of visualize happening through all these points, okay? So this would be what a positive correlation of 0.4 would look like. A negative relationship, we would just flip it so that as values on X are increasing, values on Y are actually coming down, okay? And so this is just as strong a relationship between the two variables, but one is a negative relationship and the previous one was a positive relationship. As one's going up, the other's going up. And this one, as one's coming down, the other is going up and vice versa, okay? And so an absolute value of 0.4 is the same. So -0.4 and 0.4. So the numeric value of R tells us the strength. The sign, negative or positive, tells us the direction of the relationship. So a -0.8 correlation would look like this. Again, nearly a perfect correlation or very strong correlation, but some scatter along it, and then a perfect negative correlation. Okay, and we wouldn't expect to see, again, a perfectly negative correlation unless we were measuring pretty much the same thing, okay? It's rare to find correlations above 0.98, 0.99 unless we are actually taking the same measure twice, and we wouldn't really be interested in those kinds of things. But other types of relationships we are interested in. So just to kind of have this all in one place and how we would characterize the strength of relationships based on our Pearson's R value. -1 would represent a perfect negative correlation. -0.75, less than -0.75, approaching -1, we would say is a strong negative relationship. -0.5 would be a moderate negative relationship. -0.3 would be a weak negative relationship. At that point, we start to say that there is some correlation or some inverse correlation. Below 0.3, As we approach 0, we would say that there's no relationship. And as we go to positive values, then we could say a weak positive relationship, moderate positive, strong positive, and perfect positive as we approach 1. So it's proportionate. So the absolute value of R is the strength, and the sign tells us whether they're dancing together in the same direction or they're dancing in opposite directions. As the value of one variable goes up, the other goes down in inverse relationship. So we can also perform a statistical test to see whether our R value is statistically significant. So whereas we might compare 2 group means and determine if those 2 group means were different, now we're testing to see if that linear relationship is statistically significant. So not surprisingly, the null hypothesis would be that our Pearson's R correlation coefficient is 0, that there is no correlation. And we see to what extent that's likely to be true given our data. And so the alternative hypothesis would be that R does not equal 0, that it's either greater than 0 or less than 0. So getting back to my example with height and weight from the heart data, you can see here, this is our cloud. But this time, I actually embedded the plot within a correlation statement, which is kind of nice. I can do this both at the same time. And so in addition to the scatter plot, I also get a value for the correlation coefficient. So we can see here it's positive, and it's 0.51. I'm just going to round it up there, 0.52. So that would be, based on our previous scheme, a moderate positive correlation. That sounds about right based on what we visualized. Okay, so our eyes could probably draw a line here of best fit, and you could see the scatter around that. So it's a fairly moderate correlation. A lot of other things determine weight besides height. We know that to be true, and that sounds about right. But yeah, so that would be the correlation coefficient. Notice this is a sample of 5,199 folks. That's a lot of points to draw. So it's possible that some of these points are overlaying each other to a certain extent. Notice I actually had to tell it within the correlation statement to allow the maximum number of points to exceed the default setting, which I think is maybe 1,000 points. So I actually did say, go ahead and plot it. That's not true in the scatter plot command, but when you embed it in the correlation, I actually had to tell it to kind of allow me to have this many points. So it also calculated a p-value associated with this R, this Pearson's R, less than 0.0001. And yay, it labeled it as actually as a p-value this time. All right. As you saw with the homework exercise with South's output, it doesn't consistently say p-value. It'll have some variation like prob, or in the case of a t-test, the PR less than t. So it does take some practice sometimes in finding where the p-values are in our output. Thankfully, in this case, it was a little more helpful. So p less than 0.001. So not only is this a strong or a moderate and positive correlation, it is also a statistically significant correlation. And correlations, as you get larger and larger samples, just like anything else, will be more likely to be statistically significant. In this case, the magnitude of the relationship also seems to be pretty strong. So we would say that height and weight are moderately positively correlated. Certainly, weight does not explain everything about height, and height does not explain everything about weight. But with correlation analysis, we're kind of stuck there with saying this is the relationship between the two. So some advantages of a correlation analysis is it shows the amount or the strength of relationship, and whether it's present or not. And it can be used to make some kinds of predictions based on the variables that we've been studying. However, ideally, we'd also be able to look at things like confounding and effect modification, which we're going to get to shortly with regression models. It's often easy to capture correlational data. Ecological studies, you just get 2 continuous measures and we can create a correlation coefficient. You've probably heard the phrase that correlation does not equal causation. And that's even the case when we set up a correlation. We're not, even though we specify an X and Y axis, we're not necessarily saying that one causes the other. We are simply choosing how to portray them. Conceptually, though, it would probably be best to pick one that plausibly would be predicted by the other one. But as we'll see, that is really more for linear regression when we're trying to determine what predicts a specific outcome. But the nice thing about correlation coefficients, or Pearson's R, is that because of the way the Pearson's R is calculated, it can be compared. You can compare two correlation coefficients and say something about their relative strength compared to another pair of variables, no matter how they're measured. So that's a nice thing about correlation analysis. The disadvantages of correlation is that we can't assume a cause-effect relationship. We can simply report the correlation. And it could be that there's a third variable, potential confounding factor, that we fail to account for in our relationship. And in that case, we could say that there was a spurious correlation because we failed to consider confounding. We also would potentially miss effect modifiers, things that would change the relationship between those two variables. So correlation analysis is nice, especially if we want to look at a bunch of bivariate relationships among continuous variables to see the strength of the relationship. And I do recommend doing that. And you can do what's called create a correlation matrix, where you can calculate a bunch of Pearson R correlation across all combinations of your continuous variables. It's a nice way to start sometimes to say what is related to what and how strong is it. But it kind of gets stuck there. So that moves us on to linear regression, and we're going to talk first about simple linear regression. And simple, this means that all we have is one dependent variable and one independent variable. So the same as correlation, in that we have two variables, and our outcome here is going to be a continuous measure, just like in or interval, continuous or interval, same as correlation. And on the independent variable side, we can actually include other types of variables. But now we're going to focus on the relationship with correlation. But it's pretty nifty that we can then use a linear regression model to include categorical, ordinal, and other types of measures as independent variables predicting a continuous outcome. When we do a linear regression model, it states the relationship in the original units of the variables. So the correlation coefficient actually uses standardized versions of each variable, where it first takes the mean, divides by the standard deviation, and that's what allows us to kind of make comparisons across different correlation coefficients. Linear regression, it will actually be in the units of the variables themselves. So specifically, a 1 unit change in our X variable, or our independent variable, results in some change in our outcome, okay? And that will be expressed based on the regression coefficient. The regression coefficient that we get from a regression model says how much does our Y variable change as X goes up, specifically in terms of 1 unit of X going up, and we'll see that here in a moment. So the equation for a linear regression model might look something like this. We have some dependent variable Y. We have an intercept. This would be where the line meets the y-axis. We've got a slope or a coefficient for one variable, here denoted x, and then an error term. So in this model that I'm doing here, I'm actually modeling weight as a function of height, just like I did in the correlation analysis. Notice there's a lot more output here. And instead of getting a value of 0.5, which was the correlation coefficient for this relationship, notice here I have this parameter estimate for height, predicting weight, and it says 4.17. Okay, and that's the beta coefficient for this equation. So what's that saying? Well, it's saying that as height increases, there is a positive increase in y, a positive increase in weight, just like we saw with the correlation. However, in the linear regression model, it's actually saying by how much. So for every 1 inch increase in height, we would expect a 4.17 pound increase in weight. Okay? You can see how that could be more useful, where it's actually telling us how much would y increase for each unit change in x. So it's fairly useful that way over correlation. It also performs a statistical test, just like correlation, that can tell us whether this coefficient, this regression coefficient, is statistically significant. There's a bunch of other output up here, which I'm not going to get into right now, but this is the parameter that we're interested in from this output, and it's basically saying that for every 1 unit change in x, or 1 inch increase in height, we would expect a 4.17 increase in weight. But what does the rest of this mean? We got this negative 117, a bunch of other stuff. Well, from our equation here, we can see that beta 0, that's the intercept of this equation. The intercept is when we set all of the other variables to 0, okay? Meaning when x is 0 in this case, or so when x is set to 0, meaning right at the y-axis, what would be our predicted value at that point? We've got a negative value. We'll see how that plays out here momentarily. So we should never go beyond our actual observed data. So the weight of our shortest person in our data set would be predicted based on this equation to be minus 117.8 pounds plus our coefficient of 4.17 times their height in inches. And this error term just means that we are evaluating this knowing that it's a prediction model. So we can calculate in that person's predicted weight based on their height. Okay, so the predicted weight of the smallest person in the sample would be that negative 17.8 plus the coefficient times their height in inches. That would be 96 pounds. So based on the best fitting line to our data, someone who is 4 foot 3.5 inches would have a predicted value of 9.6 pounds. Likewise, the tallest person in our data set at 6 foot 4.5 inches, or 76.5 inches, their predicted value of weight would be 201 pounds. Okay, so if you think back to the scatter plot, what we're doing is simplifying the relationship between our x variable height and our y variable weight. Okay, notice I flipped it from the previous. We used to have height as our y variable and weight as our x. But conceptually, like I said, it makes more sense to have weight as a function of height. And so the linear regression model is able to calculate the best fitting line to all these data points. And what it does is it minimizes the difference between all possible lines and these points. So we would call this the line of best fit, or in this case, the least squares, the least square difference from the line. So the person who was the shortest in the data set had a predicted value of 96 pounds. That is where they would fall if they were perfectly on the line. Where they really are was down here. They were actually quite a bit lighter than that. The predicted value for someone who is the tallest would be right here. Okay, So the observed, though, was slightly above that line. Okay, so this is the prediction line. This is our tallest person in terms of height. How do I know that? They're the furthest to the right. Okay, so this is our tallest person. And their predicted weight was right here. This is where they actually fell. Well, you might be saying, well, if we know their actual height and weight, why do we need to predict it? Well, what we're trying to do here is understand the relationship between height and weight and to model that relationship. But the idea is that we could use this model to say something about people who aren't actually in our data set, right? So we're often doing that with statistics. We're trying to estimate some unknown parameter based on our data. Same thing applies here, is that we are trying to develop a model that fits our data so that we can predict what we would expect in terms of our inputs and our outputs, or in this case, for every increase in height, what would we expect in terms of weight based on our data? And the more data we have, the more refined this line can become, or the more accurate it can become. So it did an okay job. So this linear model, it's a fairly good simplification of what's happening, and it didn't do a horrible job of predicting the weight of this person just knowing their height. So it's a fairly good representation of the data. And it was also statistically significant. Well, again, right now we've only looked at 2 variables, and we haven't addressed other things that would explain all this other variability from that line, right? And so when we get to multiple linear regression, we're going to take whatever's left, all that's deviating from that explanation line here, that could be predicted by height, and try to explain that with other variables, okay? So this is what's all this deviation from the line, we still have to explain all that variability that's left. So the regression line is, the goal here is to fit a model to the data. And again, it assumes a linear relationship. A linear model is just one of many possible models we could fit. In this course, we're going to focus on linear models. And in reality, a lot of people simply fit linear regression models, sometimes when it's inappropriate. So we need to make sure that there's a reasonably linear relationship in our data. Otherwise, it's not appropriate. We don't expect there to be a perfect fit to the data. What we're trying to do is find those best fitting lines that explain as much of the phenomenon of interest. And then we're going to take additional variables and explain what's left of that, okay? So that fact that we didn't perfectly predict someone's height or weight based on height, maybe if we knew something else about them, we could more accurately predict their actual weight. And so when we start to look at other factors, we should be able to get less variability along our lines of best fit, okay? So correlation can tell us the nature and the strength of a linear association between 2 variables. Linear regression is an equation that best describes the linear relationship between variables in terms of their original units. And as we'll see, linear regression is a much more powerful tool. We can start to add additional variables, and we can add not only other continuous variables, but we can also add categorical variables. The correlation coefficient, Pearson's R, represents the standard deviation change in one variable given a 1 standard deviation change in the other. So for example, when the Pearson's correlation coefficient equals 0.75, a 1 standard deviation change in X is equal to a 0.75 standard deviation change in Y, okay? Likewise, since correlation coefficients don't matter which ones we put Y versus X, a 1 standard deviation change in Y is also equal to a 0.75 standard deviation change in X. Okay, so regression coefficients are different because they're in the original units. Pearson's R is in terms of a standard deviation change, or a standardized variable version of X and Y. And what's nice about Pearson's correlation is that we can then use that to describe the magnitude of the relationship across different pairs of continuous and interval measures. So a 0.75 correlation has a similar meaning across other variables. When we do linear regression, it's very specific to the units that we're measuring. And so we have to rely on other tools to assess the strength of the relationship. So a regression coefficient represents the predicted change in the dependent variable given a 1-unit change in the other. So, or in the case of this example, a 1-inch change results in a 4.17 increase in pounds based on the best fitting line. However, the reverse is not true. We couldn't say that a 1 pound increase would result in a 4.17 inch increase in height. The reverse is not true. So we have to be careful to set up our data appropriately in a linear regression. So you would actually need to reverse the x and y variables to get that value for the slope of that best fitting line. However, in this case, it makes more sense to have weight as a function of height. So reversing it wouldn't really make sense in terms of a linear regression. Conceptually, in correlation analysis, there is not a true dependent or independent variable. They are simply interchangeable in terms of the calculation of Pearson's R. In simple linear regression, where we have just one predictor and one outcome, we specify the outcome variable y as a linear function of another variable x. So even though one is not proving causality and the other not, we are conceptually saying these are the things that predict the outcome. And so it's a subtle difference, but in correlation, we're not making any claims about potential direction in terms of cause and effect. In a linear regression model, you should be thinking about it as things that would cause the outcome or predict the outcome of interest. While the dependent variables in linear regression must be continuous or interval, the independent variables, okay, can include factor variables or indicator variables for categorical variables. So what that means is we could have a dichotomous variable, yes, no, in a linear regression model, and that would be acceptable, and we can interpret it meaningfully. So if you think about a dichotomous variable, it has a value of 1 and a value of 0 for yes versus no. So in terms of when we set up a model, it would be like going from the value 0 to the value 1, or a 1-unit increase in the dichotomous measure. And so we can include that in a linear regression model, which is a little bit counterintuitive at first, because when we have some of the coefficients, 1 unit might be something like 1 inch or 1 pound. In the case of a categorical variable or dichotomous variable, we're going from no all the way to yes. And so we would expect there to be a relatively big change in the outcome. And so you have to be really careful of what are your units. Sometimes the coefficients will be larger for dichotomous variables simply because where you've moved on that scale from 0 to 1 is from all the way to 0, all the way to 1. And those are the only two possible values. Whereas something like height, in terms of inches, you're talking a very small change, okay? So we can also do what's called dummy coding of our categorical variables. So if we had more than 2 values and we didn't have a dichotomous measure, we could take, let's say, a variable called obesity status that was 1 equals normal weight, 2 equals overweight, 3 equals obese. So that was just how it was coded in the data set. What we would do is create 3 separate indicator variables representing membership in each of those 3 categories. So I might create a variable called normal for normal weight, and it would be 1 if obesity status equals 1, and it would be 0 if obesity status equaled either 2 or 3. I'd also create one for overweight, and I'd create one for obese. So now, instead of having 1 variable, I now have 3 indicator variables or dummy variables, which represent membership in each of those categories. So if you're normal weight, you're a 1 for the normal variable. If you're not normal weight, then you're 0. And the same is true of the others. But when I plug this into the regression equation, I actually only choose 2 of these to put into the model. That's very counterintuitive, but there's a reason for that, as I'll show you here shortly. But whatever you exclude, so let's say I put in the dummy variable for overweight and the variable for obese. Normal weight is the reference group for the change. So compared to someone who's normal weight, what would be the expected change in our Y variable for someone who's overweight? What would be the expected change relative to someone who's normal weight for someone who's obese? Okay, so the decision about which category, levels of the category include is somewhat arbitrary. Usually there's some sort of theoretical reason for choosing it. But doesn't that seem strange that we'd only include 2 of the 3? Well, let me show you why that would be. Think about the variable sex and having 2 values, male, female. We create a variable called male, yes, no, okay? We could create another variable called female, yes, no, and that would represent the 2 categories. But we would only need 1 of those in the model to represent sex, right? We would only need either the male variable, where 1 equals yes, they're male, no, they're not, and we don't need another variable. So we only need 1 to represent the 2 categories, where the other group is the reference, okay? So the same is true when we have 3 levels or 4 levels. We're actually selecting 1 as the reference group, and then membership in the other categories is represented by the indicator variables. Indicator coding is a little tricky. It does take some getting used to, but what's nice about it is it allows us to include categorical variables in a linear regression model. So if I wanted to test the effect of sex within a linear regression model, I would simply have 1 variable representing male, yes, no, and my change in Y based on being male or female would be based on a 1 unit change. So going from 0, not male, to 1 male, that would be the predicted change in Y. So dummy variables or categorical variables, you have to think about them a little differently in the case of regression, and interpret the coefficients as basically going from not being in that group to being in that group. Whereas for interval level measures, it's a 1 unit change, so 1 inch increase. So you'll start to see that as you look at regression output. The coefficients for continuous measures tend to be a little smaller. It doesn't mean that they're less significant, it's just they're smaller in magnitude. Okay, so if we can use dichotomous variables as independent variables, can't we just make them the outcome, Y, and have the outcome be dichotomous as well? Well, you would think so, but you actually can't. And there's a reason for that. The reason is that the way that that would be interpreted would be the predicted probability of being a 1 or a 0. And that almost would work, except the way a linear model works is it wouldn't constrain Y to fall between 0 and 1, which a probability has to fall between 0 and 1. You can't have a negative probability. So linear regression would almost work for a dichotomous outcome, but it doesn't. And that's when we're going to get into logistic regression, which is a modification of a linear regression model to allow for dichotomous outcomes as our dependent variable. Mathematically, it's much more complicated. It uses what's called a logit link function. Basically constrains a predicted probability to fall between 0 and 1. The math is very complicated. But basically, it prevents us from having implausible values of Y. Logistic regression is a really important technique in the health sciences, particularly because we're often dealing with health states that we characterize as yes, no. So a diagnosis, having a disease, not having a disease, being exposed, not being exposed. We tend to think in terms of these binaries, with disease and health states. And so we're often trying to model dichotomous outcomes. Yes, they did have a surgical site infection, or they didn't. Yes, they did develop cardiovascular disease, or they didn't. And so having the ability to model dichotomous outcomes is very, very important. And that's why we're going to use logistic regression to do that. Technically, the outcome in a logistic regression model is modeled as the log odds. Probably not going to click with you, nor does it with me. I'll be perfectly honest, because that's a meaningless value, the log odds of the relationship. Thankfully, what that means is if we take the anti-log of that, we can actually get an odds ratio from a logistic regression model. You can actually interpret it. So we often ask, instead of having coefficients, we ask for odds ratios, which we can get directly from a logistic regression equation. So if we were to study the relationship between obesity and cardiovascular disease using logistic regression, to make the coefficient from that model interpretable, we express it as an odds ratio. So the actual coefficient that we got here was 0.658, which is in terms of the log odds of developing cardiovascular disease, which doesn't really mean anything. But if we take the exponent of that 0.658, the coefficient, it actually is the odds ratio, which is a beautiful thing. So from this logistic regression model, we can determine that the odds ratio, ding, 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 is 1.93 for obesity. So if you are obese, yes, no, it increases the odds of being or having cardiovascular disease by 1.93. It's a beautiful thing. Logistic regression allows us to calculate odds ratios and adjust those odds ratios by simply plugging in variables. It's very powerful. And so I could have, with a simple linear logistic regression model like this, just not use the 2x2 table. The nice thing about logistic regression is that I can then adjust this crude estimate of 1.93 by adding additional variables. So that's really the power of logistic regression, is that we can calculate a crude odds ratio just like from a 2x2 table. But then let's say I wanted to adjust for age and I just wanted to adjust for other things. I could then include those in the model and get an adjusted odds ratio, which is what we ultimately want to achieve through multivariate analysis. So logistic regression, we would rarely do a simple logistic regression model for two dichotomous variables. There'd really be no reason to just not use a 2x2 table. But when any of the independent variables are continuous or interval, we can also use logistic regression, or we can adjust for those interval and continuous measures to adjust for a factor variable. So it's really a very powerful tool, and we'll get some practice using logistic regression and linear regression next week. Logistic regression is used widely in public health, epidemiology, and medicine. Partially, this is a function of how we think in medicine and public health. Whether we should be thinking that way or not is another question, but we tend to dichotomize things. We tend to dichotomize health states, exposure status. We talk about risk of disease, yes, no. It's also common because of the way that we set up studies. Cohort studies, case control studies, cross-sectional studies, we're trying to estimate relative risks, odds ratios, prevalence estimates from these different studies, which are proportions or usually in terms of some sort of dichotomous outcome. So we use logistic regression a lot in public health and in epidemiology, and we use it to estimate adjusted relative risks, adjusted odds ratios, adjusted prevalence ratios from the different epidemiological study design. So the final week of class, I'm going to have you actually run some logistic regression models, starting from 2x2 tables. You can kind of get your head around what's happening there as far as calculating an odds ratio, and then adjusting using logistic regression. You can do adjustment through stratification, but once you max out at a couple variables, it's pretty hard to do 2 by 2 by 2 by 2 tables. So we ultimately use logistic regression to do that. It's pretty handy. So next week, we're going to focus on multiple regression. Instead of just doing linear regression with one outcome and one independent variable, we'll be looking at one outcome and multiple independent variables. We'll also discuss how to use regression to explore effect modification and to adjust and deal with confounding. And then the final lecture, we will talk about survival analysis, which, just like logistic regression, is used heavily in the sciences, particularly in clinical trials and randomized studies. We often use survival analysis because we have to stop the study at some point, and so we have to take into account data that we don't have full follow-up, and so we'll use survival analysis. Next week, you'll also do another SAS project, and then we will be done. So hopefully this week you are reading through the chapter on multivariate analysis. It's probably the most important chapter in the entire book. If there was just one chapter in the book I would highlight, it's that one. So please do read the chapter on multivariate analysis, and that'll set us up for success next week when we start to actually perform some of this analysis. All right, I hope everyone has a good week, and I'll talk to you soon. Bye.